Okay, so for now we discussed many of the theories and the concepts behind magnetism. We're going to take a little quick break from all the theories and concepts by starting to talk about how you could apply magnetism and what we learned previously about electricity to real life application and stuff that they've done before. So we have here is a picture of a cathode ray tube. Many of you probably remember the cathode ray tube from chemistry, where Thomson used this tool to discover the electron. So what we have here on this board is a drawing of it, and we'll just give you a simplified version of what's going on inside of the tube. So you have here at step 1 where the electrons are emitted by the hot filament that you have here. And then at step 2, there's an acceleration of the electron from one part to the next caused by the potential voltage difference. As you remember from previous chapters, that the electrons flow from high to low. So if you have, let's say, 100 volts on one side and then you have 0 volts on the other side, the electron will flow from the 100 to the 0 volt side. And then at step 3, you have 2 narrow beams that purposely direct the beam's pathway so it will go on in a straight path. Okay, then you have step 4 here. Step 4 is the bit more complicated part of the tube. First, take note that this side is the positive side, and then this side of the cathode ray tube is the negative side. So in this little drawing here, you see a cross field. Cross fields occur when the B fields, which are the magnetic fields, and then the E fields, which are the electric fields, are perpendicular to each other, as you can see by the drawings. The E fields right now, the arrows are pointed downward, and for the B fields, the arrows are going into the board, so they're perpendicular to each other. So, but then you might be asking, how does this direct the light? Well, for the E fields, as you could remember from previous chapters, the electrons go the opposite direction of the field. So the electrons in this case, the force would be pushing the electron upwards. For B fields, as we learned in the previous sections, that the magnetic fields force the electrons to go from positive to negative. So now the force is downwards. As you can see, that the electric fields are going upwards and the magnetic fields going downwards. This is what you create an opposition between the two forces. So they kind of stabilize the pathway of the beam of light. So now you get to step 5, where you have one spot where the light is directed. So in this picture, we have the pathway of the electron / the light going purposely straight towards one specific spot in a straight line. But you could actually change the angle of the beam just by changing the magnitude and the direction of the E and the B fields. So if you think about it this way, if you think of the E fields and the B fields as switches, you turn one on. Let's say you turn on the E field. So then once you turn on the E field, only the E field will have any effect on the particle's path. So however you adjust the E field without the B field, it will cause deflections. But however, as soon as you turn on the B field, that's when you have your opposing forces working together to direct the light. Besides in the cathode ray tube, there's other ways people have used this idea before. If you remember, well, you wouldn't remember because it was a long time ago, but in old computers, this is how they would direct certain lights on certain areas of the screen. And now, just to make it more interesting and more real life, we have a quick video of an actual cathode ray tube.